Hello, welcome to DevOps Underground. It's great to have you here with us tonight. Can you tell us a little bit about yourself?
Hello, thank you for guesting me in this meetup, online meetup. My name is Alparslan Avci, and I'm working for Hazelcast for nearly 7 years, actually, as a software developer. I'm in the cloud native team, and we are dealing with the uh, Kubernetes issues and discover plugins. And also, in lately, actually, we are developing enterprise operator for Hazelcast, Kubernetes operator. So yeah, I also like to present and talk in these kind of conference and meetups. It's really good for me. I really like it. Yeah, that's pretty much it.
Nice. And what topic are you going to present today?
Yeah, I will be presenting about distributed transactions in a service mesh. So it will be related to the large enterprise application systems which are using service meshes. So how we can how which ways of distributed transactions that we can use in these systems. I will mention about two-phase commit and distribute sagas, and I will make a demo with my custom solution.
Sounds like fun. How long have you been working in this area?
Actually, I will be I'm interested in these containerization, microservices, Kubernetes, and service meshes pretty long time, but I'm actively working in last 3 years, I can say.
Very impressive.
Yeah, thank you.
All right, the stage is yours.
Yeah,
Take it away.
thank you. Thank you very much. Let me start my share my screen. Yes, I think you can see it right now. Yes, I can. Welcome to my presentation. Uh, as I mentioned, we will discuss about distributed transactions in a service mesh. I mentioned in the beginning, but if you are recently joined, then I'm working as a software developer for Hazelcast and working with the cloud native team. As I mentioned, I have nearly 3 or more years experience with the cloud native environments. I love to solve problems if I can, of course, and you can reach me. You can send an email to me using iPerson@hazelcast.com. Yeah, let's start with imagining. Let's imagine that we are working for a large e-commerce business, and this large e-commerce business that has thousands of transactions per day, and we are selling a variety of goods. We have multiple locations, multiple time zones, multiple teams, and also in these locations there are hundreds of thousands of customers that are using our business. And we are a developer in this company, and then we have this company has more than hundreds of IT workers, and these employees are grouped in specialized teams. There are multiple specialized teams in the company, and they are distributed around the world, so they are working remotely. So one day, your CTO comes to you and just asks the question: if you would like to uh, set up our application architecture from scratch, which architecture would you choose to use it? And most likely, actually, it is already being used, but you will come to the decision between using a monolith or microservices. So would you set up your environment as a monolith, or as you create multiple microservices? And most likely, since you are a really large company and you have a large development environment, you will most likely choose microservices because you will need scalability, you will need availability, you will need fast startups on your applications, you will require really small maintenance windows. So these will be allow provided with the microservice environment architecture. So, what's the wrong with monolith applications? We use monolith applications in the past a lot. Actually, there are still some companies using monolith applications, of course. But when we consider about these kind of large enterprise companies, I think there are not much using monoliths right now. So we are not using it for in these kind of large enterprise companies because they are too large and complex. They have multiple features in them, and you need to build really large applications, and their maintenance is really costly. And also, if you would like to scale them, especially horizontally scale them, it is really difficult. You need to vertically scale them, which means that you need to invest on the hardwares instead of invest on the hardwares a lot, instead of just creating new instances. Most likely, your application is not idempotent, so there are really issues. There will be really issues if you scale it horizontally. And it also has a slow startup time because it has multiple features and multiple services that is accessing. Most likely, it might be using multiple system of records or third-party services again. So it will have a slow startup time. And another disadvantage will be the updates. Actually, you need to redeploy the whole application again on each update, which will be a really difficult issue because you will have really large, actual long maintenance windows. So as you are an e-commerce business, if you have, for instance, let's just imagine an hour of maintenance window, that might cost you a lot, and that might you might lose lots of money and value during this maintenance window. So you don't want it, and so on. Actually, most of these ones, so no need to repeat all of them again. So you choose the microservice architecture, but actually it doesn't end up there because your story just starts up actually, because right now you need to deal up with multiple services at the same or within multiple environments. So imagine that this picture actually is just a drawing. It's not provided from a production environment, but there might be, as shown here, there might be multiple front end services which is facing to the clients, and in the backend there might be multiple backend services, multiple system of records, some databases. Maybe there might be a message broker, uh, and yeah, there will be a complex system, and surely there will be some issues. So when we say microservices nowadays, actually, the best way to run the microservices is to containerize them. And when you talk about containerization, you will most likely hear two words. One of them is Docker, the other one is Kubernetes. Since we are DevOps Underground, we are talking DevOps Underground. Most likely, you already use these tools. So what Docker does is, actually, Docker, you can containerize your application using Docker, and with Kubernetes is a container orchestration tool. You can orchestrate your containers, you can manage them, you can scale them easily, and you can set up some traffic policies and others, and also use service discovery to set up your application environment. But as the number of microservices increase, you will need new tools, especially since you're a large enterprise. You are working in a large enterprise. Actually, you most likely your number of microservices requirements will increase in time a lot. Actually, for instance, I know that a company which is based in Japan, and they have more than 250 microservices in the same Kubernetes environment, and they are running more than thousands of pods at the same time. So you will there are this kind of environment will require a big maintenance. It will come with a big maintenance cost. We will mention about service meshes to figure out what we can do. So what's the service mesh? Service mesh is actually, in short summary, it's a tool, it's a application toolkit that is running on the infrastructure layer, and it provides you the it takes over the communication between services, and so with you hand over the services onto the service mesh, and service mesh control all the east to west communication among the services. So also some of the service meshes provide some ingress functions and egress functions, but their main responsibility is to handle the east-west, I mean the intra-services communication. So the main we can say that there are three main goals of a service mesh. The first one is it should provide some traffic policies uh, to route the traffic among the services. Actually, this is especially for failover scenarios, for disaster scenarios, and some blue-green deployments maybe. And most of them actually also provide out-of-the-box security on the communications. They mostly provide out-of-the-box SSL communications connections. And also they will provide some observability, which means that you can track your application traffic, and also you can visualize the applications, you can visualize the traffic, how it is running, and you can see the failures, so that it will also help on the observability side. The the main service mesh products, actually we can start with Istio, which is the right now the which has the largest user base right now. Istio, it has been developed by Lyft, and now it is an open source service mesh. It uses Envoy as the proxy. We will mention their architecture in the later slides. Uh, and also, other than Istio, we will have HashiCorp's console and also Linkerd. Linkerd is the first service mesh, first featured service mesh, actually. And they now recently released Linkerd 2.0, which is a totally completely different architecture from the previous one. These are the most popular three service meshes, and also there are many other service mesh implementations, and such as AWS's App Mesh or Kuma or Open Source Mesh, which is I think the standard of the CNCFs, actually open source mesh. So when do you need a service mesh? You are running your microservices, but as I mentioned, you need the service meshes after your number of microservices increase and at a certain point. I got this graph actually from Nginx website. I think it's really good with the representation of the cost and the cost versus the complexity graph of the microservices and the other native Kubernetes services. So imagine that you start with a single simple app. If you have just single application, single microservice, a few microservices, you will have just a small cost of operation on maintenance cost for this microservice. But if you increase the number of application, as you can see that the x-axis displays us the complexity. If the number of the applications increase, then the complexity, interdependency, and the speed of change will increase. And also, the if you use native Kubernetes proven services to maintain these applications, then the cost will also proportionally increase in time. So, but if you use service mesh, the service mesh's cost to operate is actually pretty constant, not totally constant. As you can see, there's a small slope here, but there's a little slope, but actually it is cost is pretty constant. So if you have a low number of microservices, you won't need to install service mesh. You don't need to use service mesh. But as we mentioned in the beginning, if you are an enterprise company with lots of service, lots of different teams and requirements, then you will require most likely many complex, independent, interdependent applications, and the cost of native Kubernetes services will pass the cost of installing a service mesh. And there's also another note here. The service mesh pattern is actually pretty much new, not an old one. So there, not all of the service mesh implementations are all mature right now. So as they go mature in time actually, we predict that their cost will go down. So this line will most likely in future it will go down, and you will get this break-even point in much more less number of applications and complexity. But yeah, we might resolve some issues, but we will still need to resolve more problems in our application environment, because we have multiple services and multiple system of records. This is the most important one, and especially if you are an enterprise company such as an e-commerce application, e-commerce business, and then you will need transactional operations definitely. It is easy to not so much easy, but it is easier than to manage transaction operations in a monolith application. But in distributed systems, yeah, then you will need some distributed transactions. Our basic problem is the dual write problem. What's it actually? You can see in this diagram. This is a basic diagram that shows a part of our application environment. So we will have the front end service, which provides the front end, the user interface to the user. And also we have in the backend, we have a user service, we have a product service, and we have banking service. The user service provides the information about users, as you can understand from the name. The product service provides the product information, and banking service contacts the bank and does the banking operations. So imagine that the user tries to buy a product, and when they try to buy the product, the front end service needs to communicate user service, product service, and banking service all together within the same transaction. Because, for instance, imagine that you are updating the stock of a product, but and also you are updating the account of the bank account of the user at the same time. And if there's a problem within the banking service, then you need to roll back the updates on the product service. So you need to update the stock back, the number of stock of the product. So this is the actual dual write problem. You have multiple system of records, and you are trying to write them at the same time within the same transaction, within the same transaction boundary. So let's make a demonstration to see our problem. Right now, I will show you a application running on Kubernetes environment. Our Kubernetes environment is actually a GKE, Google Kubernetes engine, which is running on the managed Kubernetes. So if I check the existing number of pods and services here, you will see just right now the Kubernetes service. And also if I can check the number of pods, you will see nothing in the default namespace. Yeah, so it is an empty. But what we have is actually we have installed Istio, our service mesh. So let's also check the services in Istio system namespace, which the Istio uses as it is for its control plane. Yeah, you can see that here. There are multiple Istio-related services: Istio D, Istio Egress Gateway, Ingress Gateway, KLE, Prometheus, and all others. So it's already installed. What we will demo here is we will have a really similar application to this one, we will have a front-end service, which will named as the e-commerce service, and we will have user service, product service, and banking service as microservices. Again, all of them are microservices. So let us also check our, this one. Check our deployment YAML, what we'll use. You can see that we have a user service, which is using the user service image, and also a service, a cluster IP service for that one. And then we have a product service deployment, which again has the product service service and banking service and the e-commerce service. And the e-commerce service all knows about these three: the user service, product service, and banking service. So let's deploy this YAML file and see what happens. Yeah, we have created our services. Let's check the service again. Yeah, we have right now 4 services installed other than the Kubernetes one. And you can see that the e-commerce services, it is the user front end service. It has the load balancer type, and you will get an external IP for that one. Let's wait for it. Let's wait for it here. Also, let me show you the pods. So again, we have 4 pods, and you can see here on the pod side, all of them has 2 containers. We will mention about this one when we are talking about the Istio's architecture. One of them will be the main application container, and the other one is as the sidecar, is the Envoy proxy container. Let's check one of them so you can see 2 containers. Yep. Yeah, here, let's find, the containers. You can see that this is the banking service, the container, and also the Istio proxy as the sidecar. So there are 2 containers here. Let's check our service again. We have the external IP assigned to this service, so we can use this one to reach our application. Let's try with the browser. Yeah, this is our front-end service. There's this simple one product exists in our store right now. This is just a sample one. And in this one, actually, you will see that there are multiple information. The first one, firstly you see the information about the product, its name, it is price 4,500, and it is product stock. So we have also in this top right corner, you can see the available user credits. This user credits is something like that. You imagine that the user applied a voucher to its account, and it has 10,000 pounds of available user credits that is ready to be spent on the store. So as you can imagine, our product information comes from the product service, and the user credits information comes from the user service. It is provided by the user service. When we add the product to our basket, and we will see, we will provide 2-3 information. One of them will be the quantity, how many ones we would like to buy, and amount from your credit, which will be deducted from the available user credits, and the remaining part will be deducted from the bank account. And this amount will be get from the, of course, you can guess that one, it will be get from the banking service. So let's imagine that we will buy 3 phones, which has a total cost of 13,500 pounds. And let's imagine that we spend 3,000 of our available credit. So what should happen here? Actually, in the backend, in our application to demo application, the banking service, when we try to deduct these, when we try to contact the bank service, it will give a internal server error. So when we get this error from the banking service, what should happen actually? The quantity should stay again 10, and the no credit should be deducted from the our user credits. Let's try and see what happens. Yeah, we have the internal server error displayed here. And when we go back and check, as you can see, we have the product stock 3 and we have the available user credits 7,000. So there's a problem. There's a dual write problem here. The whole application didn't run in a transactional way. So they are not they didn't run in the same transaction boundary. We have the problem. We have to fix this. Also, we can. I would like to show you the KL console. This console is actually the visualization of the. This is out of the box coming from the Istio. It's the visualization of the services in the service mesh. So you can see our services here: e-commerce, product, user service, and banking service. Let's increase this to 1 hour. I think, yeah. Right now, you cannot see the banking source. This is not up to date, but in a few minutes, we will see this part as red because this one will be failed. But you can see that from the outside, we get the called e-commerce service and e-commerce service called user service, product service, and also banking service. So let's continue with the problem. Yeah, to fix this problem, actually, we have to apply a distributed transaction approach. So we will discuss about two of them, two methodologies here. The first one is the two-phase commit, known as 2PC, and also the other one is distributed sagas. So when we first talk about the two-phase commit, you can imagine that you can easily guess that it is it's composed of two phases, which is the first one is the prepare phase, and the second one is the commit phase. So what happens on the background is when you have the two-phase commit, when the front-end service takes the request from the user and calls the coordinator, the 2PC coordinator. So there should be a coordinator, a single point of service here, which coordinates the whole transaction. The coordinator, when it gets this request, it starts the prepare phase. It sends the prepare request to all of the services, to user service, to product service, and to banking service. And if it gets all of them, it gets the okay, I'm ready for the transaction message from the all of the services. Then it sends the commit message to all of the services. So there are two phases in the transaction. First one is the prepare one. The second one is the commit one. So what's the issue? What's the pros and cons about this one? Yeah, oh, sorry, we didn't talk about the rollback phase. So if there's a problem on the banking service during the transaction, the coordinator doesn't allow user service and product service to commit their changes. So everything will be rolled back. The solution will work as expected. So when we come to the pros and cons of the two-phase commit, the process actually it is really good on the when you require strong consistency. You should definitely use two-phase commit approach because it is all in one. So it is a blocking application. It's a blocking approach. So it will provide your strong data consistency requirements easily, and also it will provide read write isolation when during the transaction. Actually, you won't have a false read and uncommitted read from the services. So it's also pro for the positive side of the two-phase commits. But when we talk about the cons, actually, when we talk about the negatives, it's a blocking and blocking application, which running together with multiple distributed applications is really a big problem because it means that In the distributed systems, you can have multiple issues, especially network issues. So when you have a blocking application, the blocking distributed application, you will have really big problems. And also, it requires XA compatible data sources. The data sources should be suitable for two-phase commits XA approach. Sorry. And also, there are some scalability issues because you have a single coordinator, and this single coordinator might have issues with the scalability. And also, the coordinator might fail. When it fails, actually, there will be also some issues you need to handle. The other methodology that we'll talk, and our solution will be based on also this approach, is distributed sagas. So distributed sagas is again another version of distributed transactions, but it is, when we compare it to the two-phase commit, we can say it is more available, less consistent version of the two-phase commit. So what happens here? Again, the front-end service takes the request from the user, and it calls to the services directly. But this time, the, all of the services are responsible for their own transactions. So the user service makes the transaction, and if it has any issues with the transaction, it has any problems, then it should call, in a way, the compensation call, these red ones. When it calls the compensation call, it means that it should no it should call the compensation call of the product service and banking service. So the other services should undo their operations within the transaction boundary. Let's try to make it a bit more in detail. The compensation action, as I mentioned, it's a cancellation operation. We can say that semantically it's an undoes the action, actually. And you should actually provide this compensation action within your application. It is not something like that you roll back the application action and you roll back the request and it automatically roll back. It's not like that. You need to implement the compensation action, and you need to provide an endpoint to the distributed saga coordinator or the application itself. So there are before getting to the orchestration and choreography approaches. This picture, actually, this diagram is really good one to understand the distributed sagas, since it provides a sequentially running applications. Uh, First, imagine that you are booking a trip, and in this book trip there are four microservices, four services, and the first one is for the planning the meeting. The second one will be the booking the flights, booking hotel, and booking the transport. And of course, you need to first plan the meeting, and if it is successful, then you need to book the flights. If the booking the flights are okay, then you need to book the hotel, and if it's successful, then you need to book the transportation. But imagine that you had an issue when you are booking the hotel. Then this booking hotels should cancel its application, operation, and it also needs to cancel the previous book flights and plan meetings operations. So these are the compensation calls. These cancellation operations are the compensation calls. So there are two main approaches for distributed sagas. One of them is the orchestration. The other one is the choreography approach. In the orchestration approach, we have an orchestrator similar to the coordinator in the two-phase commit. But this time, orchestration is most likely the starting application. In here, for instance, in this example, it will be most likely plan meeting. The plan meeting will manage the transaction, will manage the saga. So if there are any issues, most likely the book hotel will talk to the orchestrator, and the orchestrator will call the compensation action of the other services. When we check the choreography approach, actually, it is this time there is no single manager for the distributed saga. each application is responsible for its own transaction, totally responsible from its own application. Most likely, they are the services are communicating through a event sourcing mechanism. So, for instance, plan meetings, when it runs the application, it sends an event to the event sourcing mechanism, and then says that I completed it, and then book flies always listen the event sourcing, and so on. Actually, they will together communicate using the event sourcing, most likely, because there are multiple implementations of these approaches. The actual implementation might change. The problem with the choreography is it is very difficult to debug the problems if you have any problems, because all of them are working asynchronously without an orchestrator. It will be really difficult to see the big picture within the choreography approach. So when we come to the pros and cons of this distributed sagas, as of course the biggest positive of the sagas is this is running asynchronously. It's not a blocking approach, so all of the services are available most of the time without any blocking mechanism. And you also you don't need any specific mechanism. You don't need have a specific data store or something like that. You can have heterogeneous distributed components, such as you can have a Node.js microservice together with Java microservice, and they will run okay. You don't need XA transactions, and also, of course, it is scalable. There's no issues with the scalability. When we come to the cons, the negatives of the distributed sagas, uh, yeah, as I mentioned in the beginning, it provides eventual consistency, not a strong consistency, because the when you are running the the services, they can until you run the compensation action on a failure, that service will still provide the information within the transaction. So this means that there will be no read isolation, uh, and this might cause some issues. But since we are talking about large application environments, most likely availability will come a better approach for the requirement for the when we compared to the consistency. Of course, if you think of a bank transaction or something like that, you will need again strong consistency. So you cannot use distributed sagas. But another problem with the sagas are the compensation function development, because as I mentioned, these are the compensation actions are not just the call that you can do when you call it on the monoliths, such as the rollback or something like that. You need to implement the compensation function, and you need to provide an endpoint to the saga operator. So it might be complex and it might be costly to provide these compensation functions. And also there might be some compensation failures which will again cause issues. So the orchestrator might require a solution for that one, or somehow you need to find a solution to provide a solution for the compensation failures. So let's talk about our solution. As I mentioned, it will be based on the distributed sagas. I will call it Propeller, just as a nickname. The Propeller solution is not a production ready one. It's just for this demo purposes, and it will show us the uh, features and what we can do with the service meshes, and also in microservices, Kubernetes, to overcome the distributed transaction issue. Let's talk in the beginning. Let's talk about Istio architecture. The Istio, most of the service meshes have the similar architecture, but when we will use Istio, and let's talk about its details. Firstly, it has two planes. One of them is the control plane, and the other one is the data plane. Control plane, as its name shows, actually it controls the whole service mesh. It has multiple microservices, Pilot, Stidl, Gale, and others, and Istio, of course. and these ones actually providing discovery, configuration, and certificates and others to the data plane. On the data plane side, we have the pods, we have the services which are running in the pods. In these pods, you can see that, as we also see in our deployment, we have the main service container and also the proxy container, which is running as a sidecar to the service, the main service. In Istio, the proxy is Envoy proxy. It is called Istio proxy, but in behind actually it's based on Envoy proxy. So here you see the ingress traffic is coming from the outside of the Istio mesh, and also we are sending the egress traffic to the outside of the Istio mesh. But the intra-service communication is done through the proxies, not directly. None of the services directly communicate with other services. So we can say that the Istio service mesh handovers the communication, intra-service communication from services to its data plane. So it provides this one. And when we talk about here, our solution also based on this approach, and we need to talk about the Envoy proxy filter chains. Here, the Envoy proxy has a feature, which is a really useful feature, which we call filter chains. Uh, Between your proxy listener and your service, you can apply multiple filters, and you can call these filters in a chain in Envoy actually. So what it does actually, what these filters do, uh, or you can enrich your data, you can enhance your data, you can block it, you can cut the circuit, you can do anything with the Envoy proxy filters. There are multiple types of the filters, such as HTTP filters, TCP filters, security filters, and so on. So you can add as many as you want, and you can intercept the communication, and you can change the structure of the request, or you can get the information from the request using these filters. So when we come to our own solution, the propeller solution, again, we will have, as you know, we have three services: backend services, user service, product service, and banking service, and they are running in the service mesh. So they have Envoy proxies as sidecars. We will add a filter, which is mentioned as PF here, propeller filter. We will add a filter to the Envoy proxy filter chain, and this filter will intercept the communication between the services, among the services, and provide the information about the transaction to our propeller application. And this propeller application will collect those information and stores the transaction information in the Hazelcast cluster. Hazelcast cluster here is acting as a data store, in-memory data store. So we will use Hazelcast IMAP feature to store the data. And when we require the information, when we have an issue with the transaction, if you would like to cancel or rollback, we will get the information from the propeller app. Propeller app will get the information from the cluster, Hazelcast cluster, and sends back to the filters. And the filter will call the compensation actions accordingly. So let's make our demonstration again. So I will not redeploy the application. The application is still running, and our product stock, we can refresh it. The product stock is still 7, and the available user credits is again still 7,000 pounds. So let's check our solution. We will have the application deployment, the propeller application deployment. Here you will see the propeller app. It is using a container image, and it has a service. We will have 3 replicas of this one just to show it is distributed structure. And on the cluster side, Hazelcast cluster side, we will again have a stateful set with 3 replicas. Each of the replicas will run a single instance of Hazelcast members. And we will have a Hazelcast cluster service to access these replicas. So let's apply our, sorry, not this, no, this one. Let's apply our cluster first, Hazelcast cluster first. The cluster is being created, and let's apply our propeller application deployment. And let's check the services right now. Yeah, you can see that right now we have the Hazelcast cluster service, and we have the propeller app service here. And when we check the pods, yeah, we add 6 more pods to our environments, 3 of them for Hazelcast clusters and 3 of them for the propeller application itself. If we check the logs of the propeller application, yeah, it is running without any issues. It's a Spring Boot application, and it's connecting to the Hazelcast cluster using its Hazelcast client, Java client, and you can see that the Hazelcast cluster has 3 members available to us. So let's also check the KLE console. Yeah, you can see that we have cluster, we have the propeller app, and all of the other services are still running. What we will do is actually, as I mentioned, we will apply a filter. We will add a filter to Envoy filter chain. So how we will do that? We'll use a deployment which is called propeller filter YAML. Yeah, this filter is created, and let's see what does filter has its YAML version. Get Envoy proc Envoy filter. Yeah. Yes, here. So sorry. You can see that it's the HTTP filter, and this is inserting before the operation. So it will be running before the operation runs, and it's an Lua. It's written in Lua. There are multiple you can you have multiple options to implement these filters. I have used Lua here to make it to implement it. So there are 2 functions. First one is on running on the request. On each request, we are getting we are checking if the request has a transaction ID header, and this transaction ID with this transaction ID header, we are sending the information of the request to our propeller application. Here you can see that on the propeller application, and on the response, if we have any response other than 200, which is the successful response, if we have any errors, then we will start the rollback action. We will get the information about the transaction by calling the propeller application, and then we will get the compensation action list, and we will call all of the compensation actions within this filter. So let's see in our application again. So I will mention about this one because you see that I didn't redeploy the application itself. The application is running. We just apply the filter on the fly. So let's again try to add 3 more. To try to buy 3 phones and try to get 5,000 from our credit this time. So what we'll see if the propeller, our solution, if it doesn't work, we should see the quantities. Since we had 7, we should see an eventual quantity of 4 if our solution doesn't work, and we should see the credit as 2,000, right? But if it works, these quantity changes and the credit changes shouldn't be applied on our services, so on our data stores. So eventually the user credit should be 7,000, and the quantity should stay at 7. So let's try. Yep, we had the error, and when we go back, yeah, you can see that our available user credits stayed at 7,000, and our product stock is still 7. So what does it mean? It worked. Yeah. So we done the whole transaction, whole operation in a transactional way. So within distributed Saga. So if you would like to see what happened, yeah, the banking service application returned the HTTP 500 status to our Envoy proxy, and propeller filter, when it sees this response, it goes to it went to the propeller app and gets the information about the transaction, the compensation action call, endpoint information, the parameter information, and so on. And then it calls the compensation action of these two services, the user service and product service. So everything will be eventually go back to normal without applying any person operations. We can also check the Kiala console here. Yeah, this is right now it is getting more complex because our e-commerce service called user service and product service, and also the banking service. Here we don't see, but yeah, this is updated right now. The banking service, the filter here called the propeller app first. There's a communication between this one. This is override by the under the product service, and get the information from the propeller application, and it called the user service, product service, and itself to compensate the actions. So our solution works, but yeah, what next? Actually, as I mentioned in the beginning of my demonstration, this application is just a toy application. It's not ready for production. It has many flaws actually, which I didn't mention. For instance, what happens if you totally kill the pod that is running the compensation actions, then there will be another issue. But yeah, for this one, actually right now in Hazelcast, we are implementing an application toolkit, which we call internally Turbine. It won't be, most likely it is a public name, but we are developing it right now currently. It will be I think in a few months it will be ready for general available. So with this toolkit, you will be using orchestrator approach to implement distributed sagas, but you won't need to run it in a service mesh, which is really a good part. You don't need a service mesh to use Turbine, but of course you can use it together with a service mesh. But as we mentioned, service meshes are a bit costly to run. So it will be good to have the Turbine without service meshes. Yeah, I hope in future actually the service meshes will get more mature, and then hopefully we will be able to use their features more easily and less costly, I can say. Yeah, we can pass the questions if there are any.
Thank you. That was a great talk. Very impressive.
Yep, thank you. Let me stop the screen.
Yeah.
If I don't know if you have comments or questions.
Check on the channel. I can't really see anything. If you can't think of any questions now, of course you can always ask on the Meetup page, and we'll make sure to pass them on.
Yeah, exactly.
Right. Thank you very much. Great
Okay,
talk.
thank you. Thank you for hosting me. Actually, this is really great to be here. I hope we will be also meeting face to face in near future.
I hope so.
Yeah.
It was so much nicer. I think everyone is just longing for that.
Exactly. We missed those times. Hopefully, it will come back again soon.
Yeah. All right. Have a good evening.
Okay. Thank you. Have a good evening. See you, everyone.